Now let us take a simple example of binary logistic regression with one independent variable and then try to understand what are all the things that we have discussed so far. Let us take in healthcare data, simple same example that we have used, which is age versus disease, right. So disease is your dependent variable and age is your independent variable. Age obviously here is a metric variable and these are all the patient ID, and disease y is equal to 0 represents absence of disease, that is no, y is equal to 1 basically represents the presence of disease, right. So categorical dependent variable. Using this, when I run a logistic regression in any of the softwares, right, this is before going to logistic regression, usually they go for a scatter plot just to try to understand whether can we still use a multiple linear regression kind of thing and put a best fit line. So obviously if you look at it, so we cannot put a best fit line between these things because so this is a 0 and this is 1 and there are no values in between, right. So obviously it will not come under a best fit line, right, just to understand, and this is how the data is, and hence the best fit line or ordinary least square is ruled out. Now using the sigmoid function on logit transformation, when we run the data in any software, so this is what we will get, right. So instead of ordinary least square, what we will go for something called as maximum likelihood estimation. So let us try to understand MLR and LR. So I keep on referring MLR because that's the easy way to understand. So two techniques that is a must for everybody is multiple linear regression, logistic regression. So if I understand how the multiple linear regression works, the same thing I can understand in terms of how logistic regression works. In MLR we use a estimation method called ordinary least square estimation, right. So which basically tries to minimize the error, right. So the same logic I cannot use for logistic regression because the error here is only 2. The category 1 can be classified as 0 or 0 can be classified as 1. So there is no distribution of error itself here, right. So only 0 can be classified as 1 or 1 can be classified as 0, which is a misclassification, and hence he cannot use ordinary least square. So and hence I go for something called as maximum likelihood estimation, right. So what is maximum likelihood estimation does without getting into technicality of it? So this is what it does. It is basically likelihood of estimating the optimum coefficient is maximized because it concentrates much on optimizing the value of estimates from the sample data, right. So that is the beauty of maximum likelihood estimate, right. So coefficient is basically your beta coefficients. It tries to get the optimum coefficient based upon the data, right. So it gets whatever data you give, based upon that data it tries to get the, that is likelihood of getting the optimum estimate is maximum, right. So based upon that criteria we are using what is called as maximum likelihood estimate to estimate the parameters. So in MLR we use ordinary least square estimation, that is minimizing the error criteria, we arrive at the beta values. So here we are trying to increase the likelihood of optimum estimation from the sample data, and thereby we are getting the optimum value of beta naught and beta 1, right. This is the rationale behind why we are going for maximum likelihood estimation. So without getting into the formula part of it. Now those of you who are interested in formula, this is the formula for you, right. So log likelihood we call it. So log likelihood is a function of summation of I is equal to 1 to n sample size, yi is the value that is associated with the success class, and ln of pi of z, right, which is your logistic function, plus 1 minus yi, which is your non-success class, right. So this is a success class, then 1 minus yi is your non-success class, into ln of this is pi of z, then it becomes 1 minus pi of z, right. So when we maximize this log likelihood function, then we try to get the best estimates of beta naught and beta 1, right. So using this function which is called as maximum likelihood estimation function, we arrive at optimum values of beta naught and beta 1, right. So this is how, if somebody asks what function we use to arrive at the values of how do we estimate the parameters in logistic regression, the answer for that is maximum likelihood estimation. Now Moving further, how to interpret the relationship between the independent variable and dependent variable. Obviously we use beta to interpret the relationship. So if beta is equal to 0, that means the probability will not change, it will remain the same for all the values of your independent variable, which is x. If probability, that is beta, is positive coefficients, that is greater than 0, then the probability increases as the x increases. If beta is a negative coefficient, that is less than 0, then the probability, your dependent value, decreases as the value of x increases. So this is a interpretation. So as you have an interpretation in multiple linear regression also, per unit change in x produces how many unit change in the y, dependent variable, right. So this is the way to understand here, that is dependent variable is numeric, whereas here in terms of probability is estimated. Now let us say this is the result I have got, how to interpret the result of logistic regression. So first let us put the ground rules in place. Yi is equal to 0, denote no disease, yi is equal to 1, denote disease in our data set. So that means if I refer p of yi is equal to 1, which is my success class, as pi I, so this is my success class, and then probability of yi is equal to 0 is nothing but 1 minus pi I, that is non-success class, right. So put it otherwise, if probability of success, right, so probability of success is equal to p, then what is the probability of failure or non-success? So probability can always be 1 only, right, so hence 1 minus p. In this case, if probability of success is pi I, then probability of non-success becomes 1 minus pi I, right. So that is the idea here. Using this, what we are trying to understand, the logistic regression equation always tries to establish the probability of success class, right. The probability of success class y is equal to 1, that is with that disease is equal to s. Now this is the equation that the logistic regression will throw in. This is your age, independent variable, and this is the intercept, which is the constant. Let us concentrate on age. So this is your coefficient, this is your beta coefficient, this is your standard error, and this is the statistics that you will get. In this case, something called as wall statistics we get. In MLR we use t statistics, so in logistic regression we get wall statistics, and there is a degrees of freedom given, and this is a significance value. Significance value is nothing but your p value, right. So p value, as you remember, p value less than or equal to alpha value, you need to reject the null hypothesis. So p value here is 0.038. If you take the alpha value of 0.05, right, so alpha value of 0.05, then obviously p value is less than the alpha value, and hence I need to reject the h naught. What is the h naught here? H naught is whether beta is equal to 0, and alternate hypothesis is beta not equal to 0. So I am going to reject it. So that means what? Beta is not equal to 0, right. So equal to 0 I am rejecting it, and hence I am happy that beta is not equal to 0. So that means there is a significant relationship exists, that means the age is significant, age is significantly affecting. So in terms of logistic regression, how to write this? Remember the last equation that we used, that is ln of pi I divided by 1 minus pi I. Pi I is nothing but the success class, 1 minus pi I is nothing but your non-success class, is equal to the intercept minus 4.372 plus the beta coefficients 0.067 into age, right. So this is how you need to write a logistic regression equation from the output. How to dwell deep into understanding the relationship between the dependent variable and independent variable. Before that, how to convert this odds into probability is what we need to understand.